Hello everyone, welcome to the final experiment of the Organic Chemistry Labs. For today's experiment, we're going to be discussing the convergent synthesis of hexaphenylbenzene. All of this information can be found in chapter 41 of your textbook, pages 435 to 440. So the whole point of this semester-long project was so that you guys could understand what the benefit of a convergent synthesis is. So if we look back to all of the experiments we performed, we can see that we can break them down into two chains. In our first chain, we converted benzaldehyde to diphenylacetylene to make compound A. And in our second chain, we converted benzaldehyde to tetraphenyl cyclopentadienone to make compound B. With these two compounds, we're actually going to combine them into our final experiment to make hexaphenylbenzene. So all of this is an example of a convergent synthesis. Vice versa, we could also form hexaphenylbenzene using a linear synthesis. So in a linear synthesis, we start off with one reactant and we keep undergoing various reactions until we eventually achieve our product. So for hexaphenylbenzene, an example of a linear reaction would be starting off with just a benzene ring and adding each of the phenyl groups individually until we obtain hexaphenylbenzene. So why exactly do we want to perform a convergent synthesis over a linear synthesis? The answer yields in the yield that we obtain at the end. So we know that after we perform a reaction, we're not going to obtain 100% of the yield. We normally will get somewhere around 80% if we're lucky. So this means if we were to perform a linear synthesis, where after each reaction we only obtain 80% of the product, after 8 consecutive reactions, we would only obtain about 21% yield total. So that's not that great of a yield after performing 8 reactions of work. On the other hand, if we were to perform a convergent synthesis, instead of having one long chain of 8 reactions, we would actually break the chain up into 2 smaller chains of 4 reactions. So we can see that after each reaction, the percent yield is about the same, 80%. But at the conclusion of each of these chains, we actually combine their products to form our final product, also at about 80% yield. So when we compare the amount of final product we obtain using convergent synthesis versus linear synthesis, we can see that we actually obtain about 41% versus 21% using convergent synthesis. So this is why we try to design our experiments in a way that we can make them into a convergent synthesis to obtain our final product, just so we can obtain as much product as possible. So in the reaction to make hexaphenylbenzene, we are going to be utilizing 2 different pericyclic reactions. So pericyclic reactions are a type of reaction where the transition state has some kind of cyclic geometry. So pericyclic reactions can be either cycloadditions, electrocyclic openings, sigmatropic shifts, or chelotropic extrusions. And all of these pericyclic reactions were or at least the rules to predict and understand these reactions were discovered by Dr. R.B. Woodward and Roald Hoffmann, where they actually received the Nobel Peace Prize in 1965 for their contribution on this work. Today, these rules have become so important that they're now referred to as the Woodward and Hoffmann rules, and they can be taught. They're taught in many advanced organic chemistry courses. So here are examples of those 4 pericyclic reactions I had just mentioned. So a cycloaddition is just really a Diels-Alder reaction, where we have 2 different alkenes and combine them to make a cyclic alkene. In an electrocyclic ring opening, we break a cyclic structure in order to form a alkene structure. in a sigmatropic shift, we actually move around the double bonds around the cyclic structure. So you can see that here the double bonds move to form this compound. And finally, in a chelotropic extrusion, we break down a bicyclic compound to form a cyclic compound and some kind of byproduct. In this case, it was carbon monoxide. So for hexaphenylbenzene, we'll be using two pericyclic reactions, the cycloaddition and the chelotropic extrusion. So in the cycloaddition, we can see that our tetraphenyl cyclopentadienon will undergo a Diels-Alder reaction with the diphenylacetylene in order to form this bicyclic compound. From here, this bicyclic compound will actually undergo a spontaneous chelotropic extrusion where carbon monoxide will be removed and will be left over with hexaphenylbenzene. So here's just the, molecular orbital theory calculation of the Diels-Alder reaction of the tetraphenyl cyclopentadienon and diphenylacetylene. So you can see here that the triple bond breaks in order to form this bicyclic structure. Here you can see is that oxygen group that is found at the top of the bicyclic structure. So here we can kind of see how the reaction is performed. The first part of the reaction has a very high activation energy at 46.3 kilocalories per mole. However, we can see that there's a very steep, there's a steep slope that kind of indicates that this experiment is exothermic, releasing about 13.1 kilocalories per mole in heat. So because of this high activation energy, this means that we're going to need to basically heat our reaction quite a bit in order for the reaction to get started. And because of the exothermicity, this reaction will also generate even more heat. So for this experiment, heat is going to be a very big factor. So for the second part of the reaction, the chelotropic extrusion, here we can see that the bicyclic structure actually kind of breaks apart, releasing carbon monoxide as a byproduct. And this kind of occurs spontaneously due to the high strain that is present. So because of the high amount of strain, there's actually very little activation energy, about 1.4 kilocalories per mole. So because the activation energy is so low, this is how we can determine that the reaction will occur spontaneously at room temperature. Another thing to note is that this reaction is very exothermic, where it'll produce about 46.7 kilocalories per mole. So now the experimental procedure. You're going to be starting off by getting a 25 milliliter round bottom flask, and into this flask you'll be adding 0.5 grams of tetraphenyl cyclopentadienon and 0.5 grams of diphenylacetylene. Once these are in the flask, you're going to heat this using a heating mantle as well as stirring the mixture for about 15 minutes. While you're stirring, what usually happens is the compound will go from purple to about a brown color. So after you stir your diphenylacetylene and tetraphenyl cyclopentadienon, you'll actually take off the flask off heat and add 10 milliliters of diphenyl ether before you place it back onto heat and stir the solution again until it looks homogeneous. The reason you want to take the flask off the heat and add the diphenyl ether is because the diphenyl ether can actually inflame if it's too hot. So that's why you just want to kind of take it off and then put it back on. So once the solution becomes homogeneous, you allow the solution to cool to about room temperature before you add the 20 milliliters of mixed hexanes. it's the same thing that these mixed hexanes can burst into flames if the flask is too hot. For this one, though, we have to kind of cool it quite a bit to room temperature, or else the hexanes will combust. So once we've added the hexanes and kind of mixed it a bit, we can put it into ice, and then once it's cooled down at ice, we can collect our product using vacuum filtration. So once all of this is done, that is pretty much the entire experiment, and that would be the last experiment for the lab. So just some considerations to think about. So because this high activation energy is so high, we need to use a ton of heat in order to initiate it. So remember that the glass is going to be very hot, so you kind of want to be using some kind of clamp in order to hold them. And if you ever need to move the flask, always use tongs. Just never touch a hot flask with your hands because you will burn it. In the textbook, it says you can use a glass stirring rod, but a metal spatula can also be used. Just remember that because the glass is hot, you can actually kind of poke holes into the flask if you're not careful. Just because of how hot the glass is, we can cause it to, it basically becomes very malleable. So the diphenylether is the solvent that we'll be using to bring the reaction to completion by keeping everything in solution so that nothing precipitates. So our solvent, diphenylether, it's actually a compound that's usually a solid at room temperature. So because of this, you would have to kind of gently heat it to melt it a bit so that you can measure it properly for the reaction. So hazards, again, heat is the biggest one. You need to be aware of the fire danger when working with this experiment. As I said before, when we add the diphenylether, we need to be very careful because it can inflame if the flask is too hot. So that's why we kind of want to remove it, add the diphenylether, then put it back. And this is even more the case for the hexanes. We cannot add the hexanes if it's even remotely hot. We have to let it cool to room temperature. So once we've added the hexanes, the flask should be at room temperature, so then it should be okay to place it in ice. But just in case it's not at room temperature, a good thing to always remember is never put hot glass into ice immediately. So Pyrex glass can withstand a large thermal shock of about a change from 160 degrees. But if the shock is too fast, the glass can still break. So we kind of want that to not happen. So once we collect the hexaphenylbenzene, we would want to perform some kind of test on it by obtaining the IR spectrum, an NMR spectrum, and a UV-Vis spectrum, so that we could see how this sterically hindered structure kind of looks like on different types of spectrum. But because we won't be doing that, that's just an idea of what would be the last part of the whole lab. So with that, that would be the conclusion of the organic chemistry lab. And I hope you guys have a good rest of your day. Alright, so now let's perform the calculations to determine the theoretical and percent yield of hexaphenylbenzene. So I've already listed the starting masses of our tetraphenyl cyclopentadienone as well as the diphenylacetylene. So let's pretend we ran this experiment with the exact same conditions that were written in the manual, or I guess written in this presentation, and we isolated 0.3 grams of product. So first let's determine the theoretical yield. For us to do this, we need to determine which of the two reagents is our limiting reagent. So to determine the moles of each material, what we do is we'll divide the mass by its molecular weight. So 0.5 grams divided by 384 will give us 0.0013 moles of TPCPD. and then 0.5 grams divided by 178.25 will give us 0.0028 moles of the diphenylacetylene. So comparing the two, it's very easy to see that our limiting reagent is our TPCPD. So now that we know the actual amount, or in moles, of our limiting reagent, we can determine what should be the mass of our hexaphenylbenzene. So starting with the moles of limiting reagent, we saw that from the reaction, for every 1 mole of TPCPD, the limiting reagent, it gets converted to 1 mole of hexaphenylbenzene. And every 1 mole of hexaphenylbenzene is about 384.5 grams. So in the end, the calculation is 0.0013 times 384.5 grams, and that leaves us with 0.695 or 0.695 grams of hexaphenylbenzene, or 695 milligrams. So now that we know the amount that we should have gotten, we can compare it to the mass that we did get, which is the 0.3 grams. And so to calculate the percent yield, we'll take the 0.3 grams divided by our 0.695 grams, which was the theoretical yield, and just multiply it by 100, and we'll get 43.2%. And so so that means that after isolating 0.3 grams of product, we were only able to, I guess, yield about 43% of what we should have. So now let's look at what our spectrums would have looked like. So the spectrum you're looking at right now is for tetraphenylcyclopentadienone, the IR spectrum of the TPCPD. So the only reason is because I couldn't find a good, I guess, spectrum of hexaphenylbenzene. So instead, we're just going to do something much easier. We'll look at the spectrum of one of our reagents, which was the tetraphenylcyclopentadienone. And then after reacting it with the diphenylacetylene, which isn't shown here, we'll get the hexaphenylbenzene. And so what we lose is this ketone group, and what we get is another benzene. So if we look at our IR spectra of the tetraphenylcyclopentadienone, there was only really 2 major functional groups. The sp2 hydrogen stretch from the benzene rings, as well as the carbon double bonded oxygen stretch for the ketone. So once this reaction occurs, we lose the ketone, so we should expect a very similar looking spectrum, except this peak for the ketone should be absent. So we should only really see this sp2 carbon hydrogen stretch. And so the same thing kind of occurs with the NMR. So once we lose the double bonded oxygen, once we lose the ketone, the entire molecule becomes incredibly symmetrical, where all of the hydrogens are almost exactly the same. And remember that in a hydrogen NMR, when we look at benzene rings, the signal that we'll get is usually somewhere around 7, which is this line here. So because of the sheer amount of benzene rings, and because all of these hydrogens are pretty much the same, we would actually only really see this one very, very strong peak, because we're getting about 30 hydrogens that are being integrated into this peak. So if you compare it to something such as benzene, just simple benzene, the peaks would look very similar. However, the major difference is for hexaphenylbenzene, we are expecting 6 times the signal and the intensity, just because of the sheer amount of hydrogens that are on the molecule.